Starting. Okay, right. Yes. Okay. So, screen share. Desktop. Okay. Couple of things. There is a channel called, if you want to watch these lectures at home again and again and again, you can do so by going to this channel called SU for Stellenbosch University RW144, and all these classes that are broadcast on YouTube will be on there. Here is the last one. I hope this one freak out the people at home. You've seen it. There was ragging Scott. Scott is here. We weren't chatting today, Scott. So all the videos are recorded and online, and it looks pretty good. So I'm happy with that. So that's YouTube, and I can close that. Now, second thing, I got quite a few emails over the weekend about the test. But I told you what will be in the test tonight on Friday. And if you weren't in class, I don't mind it. I don't mind if you don't come to class. If you're watching at home, you shouldn't be here. But I'm not going to repeat what I say in class over and over and over. So I just kind of ignored those emails. Plus, they came over the weekend, and I'm not really going to answer weekend emails. Having said that, I wanted to get to them this morning, but I haven't yet. The common question was really, what work do we need to study? So, for the last time, and perhaps too late for many, the test will contain small on-paper programming questions that are similar to the easy and medium questions in the tutorials, for which the answers are online. I'll show you in a second. And also, everything we discussed in class. So that's basically chapter 3 of the textbook. Yes, except for that n-body case study. Right. Some people ask for past copies of tests. And I may put some up, but they're not going to help you because new lecturer, new test. You may feel a little more confident that you've seen a past copy of the test, but I promise you it won't really help. Now, this morning, we're supposed to start with sorting and searching. But I just want to finish up performance because I didn't do all of it last week, and it is important. I want to tell you about performance. But while I'm here, on this course info page, you'll see, oh no, you won't. On the tutorials page, you'll see the list of tutorials and the solutions for the first 4 tutorials that I've put up. I didn't want to do this because I want to reuse the program for the tutorials year to year. But that's okay. It's fun making up the tutorials, and I'll just make up new ones for next year. If I'm even teaching it, if the university hasn't fired me by then. Oh, you know, so the solutions are there, and it's all of it, except for the project problems. I'm not going to put those solutions up. I don't want to write the whole project for you. And I've also put up little discussions of anything that was particularly tricky about the tutorials. So have a look at that. Even if you did the exercise on your own and finished it, it's nice to look at someone else's code and see, oh, that's a nice trick, or I think I did it better, what have you. And I also finally, after many people asked me, put up the real answer to that project problem, which was supposed to look like that. So that's the real image you're supposed to get for that 4th problem of the first tutorial. And I know that some people did actually get this, but I think most that I've seen haven't. So perhaps should have a look again at that. Right here. One last thing. Oh, that's not it. I don't want to show that. One last thing is that I wanted to. I wonder if people can Q&A. Let me just switch this on. I think I just want to see it. So I know it looks funny and perhaps I shouldn't be doing that, but okay, so there's an area for people to Q&A. There's weird echo because I think I'm speaking through this mic and it's going up there. And that's because I want to show you the video I promised on Friday. Now we have to be very careful because I can already sense feedback. And it may just be that I blow out all of your eardrums and deafen a whole batch of first years in one go, plus everybody is watching online. So let's just see what happens if I play the video. It's not funny, it's just a kind of recruitment video for computer science, but it's still a little fun to watch. So I'll stop it immediately if anything happens. Okay, excellent. I think everything worked. Oops. Okay. And now I'm switched off the sound for the speakers, so it shouldn't be any feedback. I can speak loudly again, and I think I should still be recorded on the web, so we're all happy. Okay. I know it's Microsoft Research, but it's a fun video, and I think the original point was to show that to pupils at school or learners at school, whatever they're called, and get them excited about studying computer science. So it worked on all you guys, whatever videos you saw, and I'm very happy about that because you made the right decision. Computer science is what you want to study. Now, let's get back to the big prediction. The big prediction, okay? So last Wednesday, we were talking about performance and how to calculate performance empirically. So we ran the program a few times. We tried to find the function that predicts what the time will be for the program we're working with. And we made our big prediction that for 16,000 integers, it'll take 474 seconds. Now, that's about 5 minutes. Is that right? 5 times 6. No, that's 300. It's more than 5 minutes. So 8 minutes, thank you very much. Almost 9 minutes, 10 minutes. So I'm going to put this, I'm going to start this running. And by the time I'm finished, we should have, is it running? Yes, there we go, it's running. So by the time I'm finished, this should be finished, and we can see if the prediction was correct. And we're talking about the scientific method. So we only have one more section in this chapter about performance analysis to complete, really. And that's the idea that is computer science a science? You guys are not really doing science. I mean, our first year is devoted to teaching you to program. We've done many experiments, and our students forget almost everything we teach them. They retain no knowledge whatsoever. They don't remember any of the facts we tell them. I can tell you that Java has an assert keyword, but by the time you reach honors or when you graduate, you won't remember that. So what a big waste of money. I mean, it's terrible when you think of it. What we really try to teach you is not any factual matter. We really try to teach you to think in a certain way about problem solving. So that when you walk out of the university, you can go to a new company and they can say, we don't use Java at all, that is so yesterday. We are using C#. Yeah? And you've got 2 weeks and you learn C#, and you'll be able to write programs in C#, because you can think in a certain way about problems and how to solve them. The first year is just about learning to think that way, learning to program. And in the second year, we take it deeper and we start doing a little science, but it's not really science. It's not science like physics, because physics has theories, and they have formulas, and they can make predictions. Well, until now, I've told you that this is how we talk about our program performance. So we observe, we hypothesize some kind of explanation for the observations we've made. We predict what will happen if this hypothesis is true, just like I predicted that time. Then we verify by doing experiments and see if our prediction actually becomes true. And if it is, we've added some evidence that our hypothesis is correct. We can never be 100% sure. But if we find something that contradicts our hypothesis, if suddenly this program runs in 2 seconds, no, it doesn't, okay. In 2 seconds, we would know that my hypothesis was incorrect. We would know that this is not the formula for the running time of my program. But this is called empirical science, and people say, nah, it's all empirical, it's just experiments. This isn't science like physics, because they've got theories of relativity and what you mean. But the truth is that in computer science, we also have these kinds of theories. We also have an analytical approach to experimental, to performance, program performance. And we're not going to learn too much about it, but just enough to know that there is science. And when you get to second year, you'll do a lot more of it. And when you get to third year, you'll be expected to know it. And of course, then once you graduate, we'll expect you to not know anything. But that's just the way life goes. So we did experiment or empirical analysis. Empirical simply means hands-on. Right. So now we come to mathematical analysis. That guy you see there is Donald Knuth. He's an American computer scientist. He's probably is he the most famous computer scientist? I don't know. But he's definitely one of the most important. He wrote a kind of encyclopedia of computer programming called The Art of Computer Programming. And he's still writing it. He's working on volume 4. He looks oldish, and he is kind of oldish, but I think he'll last until at least volume 4 is done. So that's fine. Just one little note. It says here, Turing Award 74. So in computer science, we don't have a Nobel Prize. There are only a couple of Nobel Prizes. What are they for? Medicine, chemistry, peace, literature, physics definitely, and economics. What? Yes. So 6 Nobel Prizes. Peace is kind of outside. The others are all, well, literature is not science. But there's no Nobel Prize for mathematics. Why is that? I don't think his wife left him, but he and a mathematician were in love with the same woman, and she chose the mathematician against the odds. And so, this is the story. But it's difficult to think of Nobel, a peaceful, kind man who blew up his brother with dynamite. Which is why he instituted the Nobel Peace Prize to promote peace. He didn't want dynamite to be his only legacy. It's difficult to think that he would be as petty. However, that may be. In mathematics, they have the Field Prize, which is awarded to young mathematicians who make an amazing contribution. And I think a woman just won it for the first time. I think, yeah. Yeah. And in computer science, we have something called the Turing Award, which is named after Alan Turing, who kind of invented computers, and it's given out yearly by the ACM. And Turing, Knuth won this in '74 for stuff. I'm not going to tell you it. But one of his big fields that he works in is mathematical analysis of algorithms. And at least at Stellenbosch, we have one really well-known, high-level guy who also works on this kind of stuff, Professor Prodinger at mathematics. So he's kind of computer science and mathematics, but he's at mathematics at the moment. So how does it work? Well, what we do is we write a little program like that one, just 3 lines, and instead of running it for different sized inputs, we just look at it, and we count the number of instructions. We count the number of times different things happen. So in that very first line, we do a variable declaration of count, and in the second line, we declare the loop variable I. So we have 2 declarations in this piece of code. So that's why the declaration is 2 there. And we can count the number of variable assignments. Here we assign 0 to count and 0 to I. So this is also 2. Increment is counted separately. What else is there? Less than comparison. Why is this n plus 1? Surely there must be a mistake in the book. Let's find a victim whose name I can recall. It's so difficult. You all look the same to me. I can hardly distinguish you. Marie, who sits next to you? Landi. Yulandi. Yulandi. You look like someone who knows exactly what's going on. Why is it n plus 1 and not just 1? I mean, we have to understand this. I mean, it's no use just glossing over it. I can make up some excuse and you'll believe me. But when we read stuff, we should try to understand all of it. And if we just skip a little detail, we may not understand what's going on later, what's coming later. On the other hand, in my experience, when I was undergraduate, sometimes somebody said something and I didn't click what they meant. And if you wait a little while, they say something else and it all comes together. But it's really important to leave the classroom understanding absolutely everything that was said. It's no use leaving a little gap in your knowledge. You'll never catch up. So at least at the end of class, you should understand every single thing. Yolandi, why n plus 1 and not just what n? I mean, how many times is this for loop going to execute? N minus 1, yes? Baie waar. So, gestel hierdie if was nie daar nie en it was net count plus plus. Say the if wasn't there and we only had count plus plus inside the for loop. At the start count is 0, and when the loop terminates, here at the end of this code, what will the value of count be? N or n minus 1? Oh, Yolandi, I've got you out. I found your weakness. For loops. Note to self, put many for loops in test. Test. Okay, got it. Yolandi, value of count after the for loop terminates. We're pretending that if there's no if. Come on, Yolandi, we've just seen Donald Knuth. We're only on the second slide. That's guessing. Say it once again, but just this time you mean it. No, you can't say n. You say n. Okay. So why does the for loop execute n times? Obviously, for count to be n, it must execute n times. I mean, explain that to us. I mean, you said it goes to just before n. That sounds like n minus 1 to me. Is it so easy to confuse you? Okay. Okay. I'll buy that. So why is this n plus 1 then? It could be a mistake. I mean, there are mistakes in some of these slides. Marie.
Nadat dit een keer uitgevoer het, dan gaan hy dit weer getoets weer en gaan sien ook dit is nou actually gelyk aan en nie kleiner is nie. So dat na laaste keer is dat hy weer afspring en dit kan nie in.
Okay, right. So we start with I equal to 0, and then the for loop starts properly. First step, we do the test. Is 0 less than n? Yes, it is. So then we do whatever is inside the for loop, and then we do the increment. The increment happens at the end of the for loop, or each loop of the for loop, and the test happens at the start. So I'll have one test for 0, one test for 1, one test for 2, and I'll have one test for n minus 1. That will still be true. The for loop body will execute. The increment will happen. Now I is n. And then I do one more extra test. And the last test will be false. So n times, that test, that less than comparison was true because we were allowed to go into the for loop body. But the very last time it was false. And that's why there's the n comparisons, they're all true, and the very last one was false. Don't make me write it out, Yolandi. Are you kind of comfortable with that? Okay. Equal to comparison. Well, Yolandi has now Yolandi has now convinced us that even though there are n plus 1 tests, the body only executes n times. So every time we get into the body, we do this comparison to 0, and so the equal to happens n times. When we do this comparison, we access an element of array A. So array access happens n times. And the increment. Oh, Yolandi, help! Now this is less than 2n. What's going on here? Why is there a 2n? I'm going to go through the entire class and ask everyone why it's 2n. And who will know? Oh, one person will know. One person will rescue us. Who is it? Is it Simone? Simone, whatever.
N times. So you increment n in the for loop and n times again inside. So you increment 2n times.
Okay, so you are saying that this I++ here at the end of the for loop happens n times.
Yeah.
Shouldn't it be n plus 1 times? Okay, I can kind of buy that. The body is going to be executed exactly n times. And after the body, we do the increment, so that will also happen n times. And when we've done the last body and the last increment, we jump back up, do one more comparison, which is why that is n plus 1, and we see it's false, and then we don't do the body again. So the comparison is n plus 1, but the increment is only n times. Got it. Thank you, Simone. I don't know what we would have done without you. Oh, well, hang on. Count plus plus. What did you say? It's in the body, so why isn't that happening n times?
Sorry?
It's in the body, so why isn't that happening n times? But why is this less than equal to? That you don't. Oh, okay. Okay, fine. Hang on. Your hand was first. You just, I know I've asked your name a million times, and I've remembered it sometimes, but I've forgotten it today. What do you want?
Mine.
Yes, mine. What is funny name? Okay, even though the count plus plus is in the body, it's not going to be executed every single time. It's only going to be executed for those cases where AI is 0. Now, if all the AIs are 0, it's going to happen every single time. There will be n increments for the I++ and n for the count plus plus, and that'll give exactly 2n, which is why there's a little equal sign down here. But it could be that only some of the AIs are 0, or none of them are 0, in which case, even though the body executes n times, this count plus plus never happens because they're all non-zero. And then it's only the I++. So that could be as low as n. As low as n, as high as 2n. Okay. Now, who's going to volunteer for the next? Simone, where is Sean? What happened to Sean? He's part Sean! He's sitting at home, but I won't go to him now. I don't want to. Okay, just for today, I'm not going to ask people at home for questions. I'd rather ask someone in class. Josh, are you ready? Okay, prepare yourself. Next slide. Oh, no. Here we go. Nested for loops. Help. What's the problem? Look, all these values have changed. There used to be 2 variable declarations. Now there are n plus 2. What's going on? Right. Absolutely right. Count is just declared once. I is just declared once. But the body of the I for loop executes n times. And in every execution of that body, we declare j. Okay, so that's the n plus 2. Variable assignment I can live with. Josh, what is going on here? Oh, this my head is hurting. Oh, it's complicated. Josh, help. We have to understand this, because if we don't, we don't. I mean, then we're still missing something. And we'll know that if we do completely, absolutely understand this, if we can explain this, and if we can write this down on, I don't know, a test answer, then we'll know we know this. So we have to learn to understand this. Oh, man. Oh, man. Okay, right, let's try it. Let's see if we can get to it. I'm going to swap away from this now, but I'll rewrite almost all of it on my piece of paper. So today's the 25th of the 8th of 2014. Okay, right. So I'm just going to write the important part. I starts at 0 while I is less than 10. N, sorry, I plus plus. And inside here I had 4 int j is I plus 1. Oh, man. J less than n. J plus 1. Okay. But the only thing I'm interested in is the number of less than comparisons. So I'm really only interested in that and that comparison. Oh, hang on. Just give me one little second. Oh, color coding. Why hadn't I thought of this before? It's going to be so exciting. Blue. Okay, right. Who's going to help me? Well, Josh, you were helping me. You're being so clever. So I'll help you. I'll give you the target. Our target is to get to n plus 1, n plus 2, all over 2, less than. Okay, Josh. How many times will this first less than execute? Clever, okay? Right. So we already have that, okay? Let's think about this inner for loop. If I 0, then J is going to start at, Josh?
At 0. Wait, at 1, sorry.
Okay, 1, and it's going to go up to n. So how many comparisons here?
N.
Okay, n. The for loop here because I started at 0. Okay. The next time round, I is going to be 1. J is going to start at, Josh?
At 2.
Up to that. How many comparisons?
N minus 1.
Ah, okay, now it becomes clear. I is 2, I can fill this in. I, J is 3, J listen, so n minus 2, and all the way down to I equal to n. Is that right, Josh? What will J be?
N plus 1.
No, it won't.
It will break at the comparisons.
I will never be, well, I will be n, but that will be false and we won't go into the body, so J won't be anything. But if I is that, then J will start at n, J less than n. How many comparisons, Josh? 1 or 0? Okay, 1. Because J becomes n, we check is J less than n, so we do the comparison, we see it's false, and we never even execute stuff. So n minus 1, oh sorry, 1 comparison there. So this really, the number of less thans is really this sum plus that sum. Well, that. So let's just rewrite. 1 plus, above it will be a 2 plus but, n minus 2 plus n minus 1 plus n plus n plus 1 equal to, Josh, how do we calculate this? Say again, sorry? A Riemann sum. What's a Riemann sum?
The sum of I going from I to n plus 1. I equal to 1.
I don't even know that term. Are you sure it's a Riemann sum? It sounds more like a Gaussian sum. I don't know, but I mean, Gauss is the guy who invented this. Well, kind of. Do you remember that story when he was at school and the teacher asked him to count up all the numbers from 1 to 100? And he clicked that if you add 1 and 100, you get 101. If you add 2 and 99, you get 101. If you add 3 and 98, you get 101. So if you add the first 50 numbers to the last 50 numbers, match them up properly, you get 50 times 101. And we can, did you do this kind of stuff at school? Arithmetic series. You know the whole formula? Okay, I won't repeat it. So you all know it's the last number and the last number plus 1 divided by 2. Yolandi, did you do this? Do you know this? Did you do this at school? Okay, right. Let's quick overview. Oh, sorry. I'll repeat. Yolandi, did you do this at school? Okay. So just a quick overview. Let's just see. I want to find the sum S, which is 1 plus 2 plus bada until n, small n. So I can write out exactly the same sum, n plus n minus 1, but just in reverse, plus 2 plus 1. I add up these two. 1 plus 1 is, oh sorry, n plus 1 is n plus 1. That's n plus 1. This is n plus 1. So, and this is 2s. And how many of these are there? N of them. So 2s is equal to n times n plus 1. And the sum I'm looking for, n plus 1 divided by 2. Okay, basic mathematics. I'm sure you did it at school, Yolandi. Where did you go to school? Isn't that a prison school? I must be thinking of something else. I'm sorry. Okay, right, okay. Now, okay, we have 15 minutes to do lots of stuff. Let's just get back to our slides. So Josh helped us to explain why that is like that. And I'm not going to do it now because it'll waste just too much time. But you ought to do it when you get back home. I know how you guys work. You don't go to all your classes. I know that after this class you rush all the way back home. Just sit down in front of these slides and just stare at them for hours. So please do that now, again, today, and figure out why all these numbers are what they are. Okay. We have to get to this story. It's called the Tilde Notation. It's a way of talking about all these sums that we've just calculated by hand. We're still going to do it by hand, but basically what we do is, if we have a formula like this, say we calculate the time for our program to execute and we get a formula like that, for small n, this formula is important. But when n gets bigger, you'll find that these terms, and this term, the constant, and the lower order polynomial terms, they don't really matter. If you calculate this formula for a big N, this one on the left-hand side, the one on the left-hand side, the 6n cubed plus 17n squared plus 56. If you take n equal to 1,000, and you calculate this, and you just calculate the first term, the one with the biggest exponent, you'll find that they're roughly about the same. These lower order terms simply don't matter. So it's very convenient for us to compare two algorithms. Even though the time function may not be identical, if the biggest terms are identical, then we know that these two algorithms will execute in roughly the same time. So all three of these formulas are really the same as 6n cubed. And that's why we use the Tilde notation to mean that roughly the same as. And how we find it is by simply throwing away the lower order terms. So fn is roughly the same as gn, really means that if I divide them, then eventually they come out to 1 in the limit. I think this is too technical for you guys, and you don't have to know this formula. So this won't be appearing in any test you'll ever see. But this idea of roughly the same will, and it's really important in computer science, and it's part of the science of computer science. So we try to classify all the algorithms we come across, all the ones we know, into one of these groups. We say it's an n cubed algorithm, or it's an n squared algorithm, or it's an n algorithm. We call that linear time. Or sometimes it's a 1 algorithm. It's still the 1. It just takes constant time. Here are a few examples. Let's go here. So if I have a constant time algorithm, it's this little graph here at the bottom. It means that it doesn't matter how big I make the input. It always takes exactly the same time. It will always take some small constant t. No matter if I give it 1,000 or 1,000,000 numbers. And if the function is roughly the same as, so it's still the logarithmic, so it's roughly log n, if that's the biggest term, then I've got a logarithmic time function, and that's almost the same as constant. It doesn't matter how big I make the input, it just takes a small amount of time. Obviously, these are the two kinds of algorithms I want. I want all my algorithms to be constant time or logarithmic, because they're so cheap. Doesn't matter how big I make the input, they always go quite fast. Okay, next step is called linear, which is the tilde n. So if I give it 1,000 inputs, it'll take 1,000 time units. If I make that 1,000,000, it'll take 1,000,000 time units. If I give it 1,000,000,000, it'll take 1,000,000,000 time units. It's linear in the number of inputs. I'm still happy with that kind of algorithm because I can at least predict very well how long it'll take, and if the input is twice as large, it will take twice as long. Then there's something called linear arithmetic, which is n log n. That's still fine. But then we get to quadratic and cubic and exponential. And these are beginning to be really bad time functions. I don't want any of my algorithms to run this long. Because what it means is that if I give it 1,000 inputs, it'll take roughly 1,000,000 time units for squared. If I give it 1,000,000 time units, it'll take 10 to the 12 time, sorry, if I give it 1,000,000 inputs, it'll take 10 to the 12 time units. It always squares the number I give it. How long are you prepared to wait for the program to finish? Let's say you go to the ATM. Let's pick some person whose name I can't recall. Taylor. Taylor? Tyler. Tanya. No, I'm looking for Tyler. Isn't Tyler? I'm sure there's a girl called Tyler. What? You know her? Nobody knows her. Nobody's seen her. But okay, Tanya, I'll settle for you. Tanya, you go to the ATM. How much money do you typically take out? 200 Rand. And what's the PIN number again? No. 200 Rand. How long does it take? Say again? 20 seconds. That's excellent. So let's pretend that it's a quadratic time algorithm that the bank uses at the ATM. If you want to withdraw 400 Rand, are you prepared to wait 2 minutes? What about 20 minutes for 600 Rand? Can we tempt you with that? You'll take it. I'm not giving you the money, it's your money. I'm not paying you to wait. No, okay. How long does it take to withdraw 400 Rand? Okay, same time. And 600 Rand, I'm guessing same time. It takes a fraction longer, doesn't it? Because also those machines always go while it's counting the money, don't they? I'm guessing they're counting slower for a few notes. But in any case, so what kind of function do you think that is? Exponential, cubic, quadratic, linear, logarithmic, constant? Okay, that's basically constant time. Right. Let's see if we can find a nice natural example of a linear function. So, Tanya, with all your money, you go to the shop in the Nielsen, and you're standing in a queue. Let's say there's one person in front of you, and it takes a minute. You've been to the shop many times. On average, it takes a minute to serve that one person. If there are 2 people in front of you, how long do you expect to wait? 3 people? 4 people? It's not suddenly 50 minutes just because there are 4 people instead of 3. So that's a linear function. Every person takes about the same average amount of time. Okay, now let's think about something that is quadratic. Any suggestions? Your real life, something that takes quadratic time. Who of you does physics? Okay, almost everybody. Anything in physics that's quadratic? Aha, projectiles. So if you, I'm not going to do the throw the ball into the air, because that's not intuitive enough. And in fact, my real example won't be intuitive either. But just an example. Almost all motion in physics is based on differentiation and integration of these simple formulas, which says that acceleration is linear, no, acceleration is constant, speed is linear, and actual position is quadratic. So that when you are in a queue at a traffic road, the way that people start their cars, the way they accelerate away from the traffic light, means that if there are 2 cars in front of you, you can wait 4 minutes. If there are 3 cars, you wait 9 minutes. If there are 4 cars, you wait 16 minutes. And traffic is, in fact, a quadratic function of the number of cars on the road, because it has to do with acceleration. And there's a slight delay that comes into it, which goes into that. Okay, so I want to kind of give you a kind of intuitive feeling, but you'll come across these functions many, many times, and you'll get to know them. So that's fine. Let's just see here what they say. So they don't really have natural examples, but this is the bottom line. I've got my different growth orders, as they're called, different functions: linear, quadratic, exponential. Guys, I don't mind if you mumble, but you must mumble at the right frequency, because I've got very sensitive ears. Okay. And at certain pitch of voice, so it drives me insane. Also, everything you say is recorded on YouTube. I listen, and it's very sensitive. I can hear every word everyone's saying. Okay? So just don't say your PIN number. Ian. The program I started earlier. Yes, thanks for reminding me. Let's have a look if it's finished. Oh my God, it's done. What did I predict? 43. That's our prediction. Real time, our IT real of 16 was 423 point. I trust you. 8 seconds. Okay. So how far was I out? How much percentage? That's about 50, which is about 1/8 of 400, which is roughly about actually that belongs there. So my prediction was 112% of the actual running time. And I could probably have gotten a little closer if I ran this as well and used this in my calculations as well. But that's not bad. Okay, right, just back to this. Last slide, we're done. So I have a linear function. If I increase the problem size by a factor of 100, I make the inputs 100 times more larger. How much longer do I have to wait? A few minutes. If it's quadratic, I'll have to wait a few hours more for my program to finish. This is Tanya at the ATM. If it's cubic, she'll have to wait a few weeks for her money. If it's exponential, she'll basically have to wait forever. Okay. Whatever 2 to the 200 rand is, that could be 20 seconds. 2 to the 400 rand will be, let's say, 20 billion years. Roughly speaking. Basically forever. Okay, thanks guys. So I'll see you on tonight. I'll see you on tonight at 7 o'clock. 107. That's the end of the hangout.